Welcome to my presentation. In the first lecture, we had already established that inertial systems are completely equal to mathematics on paper and in linguistic reality. This presentation is about the effect that can be observed during rotation. Effects that can affect length, the ticking of clocks, and their measurement. We use atomic clocks. The ticking of the clocks should be counted according to the defined second. Again, this is illustrated by means of Minkowski diagrams, as they can be used to represent unambiguous events that apply equally to every observer. The unambiguous events arise from the encounter of observers or the sending and receiving of information, for example in form of light signals. Everything that has happened between these intersections must have happened exactly the same order for all observers, or one completely questions the causality. In the following images, the point of area just mentioned is highlighted with yellow fields. Here in the first picture, we have the Minkowski diagram with the x-axis as the one-dimensional spatial axis, and the t-axis as the time axis for the clock of the central observer B0. To B0 rest the observers B-1 on the left and B0.6 and B1 on the right. They are named after their distance in light seconds from B0. Accordingly, additional observers can be inserted or thought. C0 is supposed to move through this system at a speed of 0.6 times the light speed. After the encounter of C0 with B0, 1 second of B time later, C0 encounters B0.6, marked with a red ring. If we want to compare the ticking of the clocks of B0 and C0 with each other, we can only make this clear at the first encounter. At the encounter of C0 with B0.6, we need an auxiliary construction for spatial simultaneity in order to compare the clocks with each other. Between the events marked with green dots, the clock of B0 has ticked for 1 second. Between the events marked with blue dots, also the clock of B0.6 has ticked for 1 second. Between the events marked with red rings, the clock of C0 has ticked only for 0.8 seconds, which is corresponding to the Lorentz transformations. This must apply to all observers in the same way. But the lower green and blue marked events, and accordingly the upper green and blue marked events, do not have to have happened for all observers at the same time. Thus, this comparison only applies to the B observers. C0 will also be accompanied by 2 observers. The train of C observers should have the same distances as the train of B observers at rest. When the C train passes the B observers with 0.6 times the light speed, the B observers have to measure the train shortened, according to the Lorentz transformations. They do this because of the encounter of B0 with C0, the encounter of B minus 0.8 with C minus 1, and the encounter of B0.8 with C1 are simultaneous. Up to this point, everything is exactly the same as with inertial motion. But now let's wind the whole thing to a cylinder. Technically feasible, for example, by trains that move along the equator of a planet that has no atmosphere and by light signals that are directed into the circular orbit by mirrors. The whole thing could also be carried out far away from larger masses with lightweight rings. We do this to avoid gravitational effects. The rings should have a circumference of 1 light second. Since the distance from B-1 to B0 and B0 to B1 is 1 light second each, the observers are then directly next to each other. They also have the same world line in common. This means that the events marked with green dots are the same. This applies accordingly to the events marked with the black dots and those marked with the red dots. Since these events take place at the same point in space, they are actually simultaneous for all observers. For better understanding, let's have a look from the top of this. It represents the simultaneous events at time t equals 1 in the B system. The yellow marked point is the middle of the B train, where B0 and C0 meet at time t equals 0. Right next to it is the observer B0 at the head of the train and the observer B-1 at the end of the train. Parallel to it, the C train runs at 0.6 times the light speed. In this case, there has been an actually unambiguous length contraction for all observers. This also detects C0. At rest, he was at the same point in space with observer C1 at the head of the train and with C-1 at the end of the train. With increasing speed, they have moved away from him, so that now at 0.6 times the light speed, he has to go a quarter of the distance to C-1 backwards to meet C1, or a quarter of the distance to C1 forward to meet C-1. The distance to C1 to the front and to C-1 to the rear will be reported in a moment. What about the light signals and the speed of light? The B train should not circle in the surrounding universe. Then the observers looking out of the window always see the stars at the same angle. In the left part of the picture, we can see the Minkowski diagram. In the picture on the right, the two-dimensional image, but several times levels on the top of each other. Here is a lightning propagation from t equals 0 to t equals 1. For this turn, the light signals emitted at B0, event marked with a black dot with a red ring, arrive simultaneously at B-1 and B1, marked by the green rings. However, observer B0 is also located at this location. The arrival of the lightning components is simultaneous for all observers, as they take place at the same time in the same place. From the right image, it can also be seen that in the left image, the events taking place in the area between B-1 and B0 run parallel to the area between B0 and B1. This makes them comparable with only minimal spatial distance, as between two trains running on parallel tracks. A lightning bolt that propagates along these trains always reaches both trains. That's why the lightning components in both directions are shown here twice. After all, they are not only given by B0 and C0 together, but also together with B1 and B-1. Reflected in the events marked with green rings, they arrive again simultaneously at B0, B1 and B-1, marked with a blue dot. Since they are also reflected by B0 in the principle, the time period from t equals 1 to t equals 2 looks the same. The development of events will still be measured from the B system. How are these events then classified from the C system? Just as with inertial motion, the flash emitted by the encounter of B0 and C0 can be reflected by the observers C-1 and C1. Then it arrives again from both directions at the same time for all observers at C0. Between these events, the clock of C0 has performed ticks for 2 seconds for all observers. Because the light signals need 2 seconds for the way from C0 to the other observer and back again, he measures the distance between the observers C-1 and C0, as well as between C0 and C1 with 1 light second, or the length of the train with 2 light seconds. The clock at C-1 and C1 can also be set to the time value 1 for the reflection event, which would correspond to Einstein's definition of simultaneity. Then in the C system, the speed of light is measured as equal in both directions. On the right side, the events are again displayed in a rolled-up circle. However, since the C train is now moving, only the events at a certain B time are displayed. Here at the time t equals 0. Here the C train has moved while the B clocks have ticked time for 0.5 seconds, or the clocks of the C observers for 0.4 seconds. In the B system, this corresponds to a distance of 0.3 light seconds or a rotation of 108 degrees. Here, both lightning components reach the observer C-1 from both directions at the same time. The incoming part of the lightning bolt is reflected, since it comes from the middle of the train. This means that both lightning components now continue to move together in a front counterclockwise. The clock of C-1 shows the time of 1 for this event. From the point of view of the B system, the clock of C0 shows the time 0.4 and the clock of C1 the time of minus 0.2 at the same time. After the B clocks have ticked for another 1.5 seconds, or the C clocks for 1.2 seconds, the C train has moved up to here. Since the last position, this corresponds to 0.9 light seconds, or a rotation of 324 degrees. The clock of C1 shows the time of 1 for this event. From the point of view of the B system, the clock of C0 shows the time 1.6 and the clock of C-1 the time 2.2 at the same time. Again, the B clocks tick on for 0.5 seconds and the C clocks tick on for 0.4 seconds. Now the lightning components reflected in both directions arrive at C0 at the same time. The clock shows the time 2. The simultaneity plane of the C system at its time t stroke equals 1, displayed on the clocks, shown with a red line, is also included in the next image. This picture could already be seen in the lecture on the comparison of inertial systems. On the left, the events are arranged from the point of view of the B system, on the right from the point of view of the C system. But the events are the same in both cases. The left and right image differs only in which events are considered simultaneous. That just depends on what time is set on the watches. Here I would like to make clear once again the difference between the linguistic reality and the reality of the universe around us, which is independent of human thought. Just because we advance the clocks 1 hour in spring no clock changes its tick sequence or the number of ticks it had performed between events. The Earth also does not change its revolutions. The time with which we then name the temporal events is only a linguistic change. This changes the measured value, but not the thing itself. However, such a change in information can also have consequences. Almost everyone gets up an hour earlier. But this only happens because we humans react to such linguistic changes and physically implement them in the reality of the universe around us. Depending on the time set on their watches, the observers compare different sections of the world lines of the clocks. On the sections of the world lines of the clocks of B0 and C0, marked here with a yellow background, both clocks have each executed time ticks for 1 second. From the encounter of B0 with C0, C0 compares the section of the B0 clock only up to the blue dot, with its own section on which its clock has ticked for 1 second. That's why, from his point of view, the B0's clock goes slower. B0 compares the section of the C0 clock only up to the black dot, with his section of which his clock has ticked for 1 second, which is why, from his point of view, the clock of C0 goes slower. During the passage of the B system with the C system, all observers meet. Between these encounters, all observers can count a certain number of ticks on their clocks. This number is valid for all observers. However, these encounters are assigned to different time displayed on their watches. This also results in the different length measurements. On the X-stroke axis, T-stroke equals 0, all simultaneous events for the C system at the time T-stroke equals 0 are shown. Since the encounters of B1 with C 0.8 and B-1 with 0-0.8 are within the distance from C-1 to C1, the C system measures the distance of the B observers as shortened. On the x-axis, t equals 0, all simultaneous events for the B system at time t equals 0 are shown. Since the encounters of C1 with B 0.8 and C-1 with B0 minus 0.8 are within the distance from B-1 to B1, the B system measures the distance of the C observers as shortened. All of these events occur in the same way during rotation. However, these events are extended by additional contacts during rotation. When C0 himself encounters B0 again, he can determine that between the first encounter with B0 and the current encounter with B0, his clock has only ticked for 1.333 seconds, but the clock of B0 has ticked for 1.666 seconds. So his watch clearly went slower, or from his point of view, B0's watch was clearly faster. The events marked in yellow are the same. This means causally that the event marked with a black dot cannot have occurred at the same time as this event because it has already happened in B0's world line. Thus, a spatial simultaneity, according to Einstein's definition, can be causally excluded. Also, C-1 at the end of the train has passed B0 long ago. Thus, even from the point of view of C0, the distance between him and C-1 must be shorter than the distance between B-1 and B0. In the case of rotation, according to Einstein's definition of simultaneity, The moving observer can set his clocks so that the non-rotating observation system is measured with the help of atomic clocks and light signals in the same way as he himself is measured by the non-rotating system. However, there are unambiguous events that causally refute this spatial simultaneity. In summary, the following statements are made. First, the faster an observer circles with his ring, the more the aberration increases and thus the distorted look of the universe. The same goes for the spacefaring twin. The faster it moves away from the Earth's twin, the more the distorted look of the universe increases. Second, the same applies to the asymmetry of the radiation originating from the surrounding universe. 3. With today's measurement accuracy of satellite navigation, the Sagnac effect is also measurable in the partial sections. There is no such thing in rectilinear movement. 4. When circling, the observer's clocks actually go more slower the more he sees the surrounding universe distorted by the aberration. The fact that it should be different with the rectilinear movement cannot be refuted by measurement to this day. 5. When circling, there is an actual length contraction corresponding to this movement. The fact that it should be different with the rectilinear movement cannot be refuted by measurement to this day. 6. In rotation, there is no question of when a ring rotates or when there is no centrifugal force. The dipole of the cosmic microwave background gives an indication of the tangential velocity. Taking into account the dipole caused by the Earth's motion, it can even be determined exactly. Unfortunately, it is not a means to determine the rectilinear motion to what causes the centrifugal force. 7. The rotating ring slows down according to the thermodynamics. The non-rotating ring will not suddenly start rotating. It can be assumed that the same is true for the spacefaring twin, and that it will slowly lose speed, and the Earth's twin will not suddenly start moving. 8. Under Einstein's definition of simultaneity, the measurement results are the same for circular and inertial motion. In order to comply with this definition of simultaneity, only measurement results that are covered by it may be used. So every lap of another observer must first be moved back before its re-encounter can be counted. It does not matter which observer spends energy on the reverse movement. Who expended energy to turn back, his clock actually went slower, as in the twin paradox for inertial motion. He changes the rotating system, so to speak, just like the twin who spends energy on the reversal and thus changes the inertial frame. In the case of rotation, however, it is clear in each phase whose watch actually goes slower, because with each lapping, a direct and thus unambiguous clock comparison is also possible. However, this comparison of clocks does not take place within the framework of Einstein's definition of simultaneity. More on this in the next lecture. 9. The measurements just mentioned causally refute that in the rotating ring the spatial simultaneity corresponds to Einstein's definition. Therefore, spatial simultaneity in united time coordinated (UTC) does not correspond to Einstein's definition of simultaneity. In general relativity, one tries to solve the problem by taking a clock imagined in the center of the Earth as a reference point. Around this clock, the clocks on Earth move and thus go slower. The clocks moving westwards move not so fast relative to the central clock than those moving further with the Earth, which is why they tick faster. But what determines whether something rotates or not? Let's imagine two bars. In the middle and at the ends of them there are clocks. The bars rotate around the middle clock at different speeds. What determines which clocks go slower and to what extent? And how does this happen? No matter what determines the centrifugal force, let's now assume that the black bar does not rotate and that the green bar rotates. What about the watches E0 and E1 shown here? Both are located in an inertial frame. Since B0, B1, C0 and C1 are at rest to E0, they are in the same inertial frame. Since D0 and D1 rotate to them, they actually go slower for all observers. From the point of view of the D0 and D1 clocks, the other clocks also go faster. Since D1 and E1 move on an almost identical trajectory, both are also measured as ticking more slowly to almost the same extent. What does this look like from E1's point of view? Since E0 and E1 are in inertial frames, E1 can also consider the clock of E0 to go slower. In any case, the clock of D1 actually goes slower than the clock of E0, and that for all observers of this universe. So it would have to be stated that D1's tick slower than E1, even though it hardly moves relative to E1. A crucial point is all observers have set their measuring instruments or imaginary measuring instruments for spatial simultaneity in the same way. Only E1 set them differently. Since the setting of the measuring instruments has no influence on the ticking of the clocks, but only on the measurement results, it is not surprising if E1 achieves different measurement results than the other observers. My question is, what unambiguous argument contradicts the idea that during rotation the slow ticking of the clocks is caused by the moving relative to the gravitational field? Of course, this must also apply to rectilinear or inertial motion. This would actually slow down the E1 clock. The speed of light would then not be a superordinate quantity, but constant to the gravitational field. Even if we do not yet have a way to measure rectilinear motion, the assumption of this possibly could be a basis for looking for one. In order not to make the lectures too long, I will stop here. It will follow the lecture Slow Transport of Clocks, which actually belongs here. For constructive criticism, the email address physik@dharma.de. And further information under www.dharma.de/physik. Thank you.